Hello and welcome to the Open Heat Transfer course Conduction. This course is brought to you by RWTH Aachen University and the University of Twente. My name is Wilco Roos, and in this video we will look how an unsteady heat transfer problem can be solved using a dimensionless form of the equation and the Heisler diagrams. The learning goals of this video are as follows. First of all, we will look which dimensionless numbers are relevant for the transient heat conduction of a body with an external heat resistance. Then we will look how the solution of the problem can be accessed by utilizing given diagrams, so-called Heisler diagrams. And finally, we will look at an example how to utilize the Heisler diagrams to obtain the temperature profile inside the body as well as the heat that is released from the body over time. Now, I would like to go back once more to our sheet, which shows the different solution procedures. Now, today we are here in a non-homogeneous body temperature with the temperature inside the body having already changed. So we do not look at an infinite body. We look at a finite body which center temperature has also been varied, and we look at the case where an additional convective resistance is present. So this is more or less a real body problem. Let's look at two different problems here, system A and system B, and check whether those problems are similar or not. So on the left side we see a stainless steel plate, 18.5 millimeters in thickness, a high heat transfer coefficient due to the water of 400 watt per meter square Kelvin. And on the other side we have glass, which has a very poor thermal conductivity, and also the air, which has more or less also a poor heat transfer coefficient compared to water. And the question is now, are those problems similar or not? In order to look at the self-similarity of those problems, we start looking at the conservation equations, and we would like to address the relevant dimensionless parameters. The equation is here what we can see, the unsteady term, and we account now for heat transfer in all three directions. So the solution of this equation will be at the end a temperature depending on the location x, y, z, which also depends on the time, on the properties of the material, and on the initial condition, as well as the boundary conditions, where here our alpha, the heat transfer coefficient, and the ambient temperature come in. Now we can transfer the equation and also the solution in a dimensionless form. So in order to do that, we introduce the dimensionless variables and we bring them all to one side, and we see that the equation itself is only dependent on Fourier number. We have done that in more detail a few lectures before. But not only the differential equation can be brought in dimensionless form, but also the solution. So the temperature T is not T anymore, but the temperature theta, which depends on the initial temperature difference. So it has something of the initial condition inside, and the boundary condition will translate to a bio number, which sets into relation the resistance inside the body and the resistance on the outer side. So for the example of a quenching steel plate, we had introduced the dimensionless parameters depending on the thickness of the plate, dimensionless time. Now the theta parameter, so the dimensionless temperature, as mentioned, is the temperature being dependent on the initial temperature difference between the body and the ambience. The bio number as alpha times delta divided by lambda, so the resistance outside divided by the resistance inside the body, and of course also the Fourier number. We can calculate all those values for the case, and then we can look how does the temperature of the body evolve over time. So we have two relevant dependencies, the bio number and the Fourier number, which comprise all the relevant information, so the body properties as well as the outer boundary condition. Let's look at plate of infinite expansion on the lateral parts. So it's infinitely high, and in depth is also infinite. Only the thickness here is meant to be d and not finite. How does the temperature develop over time? Of course, we start with an initial temperature T0, and we will eventually approach the temperature T ambience. Let's now try to bring this in a dimensionless form. So we start with introducing the dimensionless temperature theta, the center temperature minus the ambient temperature, divided by the initial temperature minus the ambient temperature. In this scaling, we start from 1 and we go to 0, independent of the temperatures that the body has and independent from the ambient temperature. And the time we also rescale using now the Fourier number, which is the dimensionless time of the object. Now, having those two new variables or dimensionless variables, we can also plot this in a logarithmic scale. So let's do the Fourier number in a logarithmic scale. Let's also do the dimensionless temperature in a logarithmic scale. And what we see now is a line that is going from 1 towards 0 over the logarithmic scale of the Fourier number. This line is now valid for a very specific ratio of the internal and external resistance. So it's valid only for one bio number. If we have another bio number, we will of course start with the same value of 1, but we will approach the value of 0 much faster. So if we reduce the external resistance, the process speeds up, and as such here we see that the chart of curves goes towards a steeper slope. The maximum slope, of course, is given if the bio number is infinite, or 1 over the bio number is equal to 0. In this case, the heat transfer coefficient on the outer side is infinite, meaning that we directly impose a wall temperature. So beyond the blue curve here, there will be no other curve available. This is the limit of the cooling down process of the object without an external resistance. Now, this diagram, which I draw by myself, can be now drawn with real values, and we can see again here the Fourier number, the temperature, dimensionless center temperature of the object, and also the bio number. And we can see here in this diagram a chart for a plate of the thickness 2x, and we can use this to calculate the center temperature over time. Now, how does the local distribution of the temperature looks like? So if we have an external and an internal resistance, our temperature looks like this. We have a decreasing temperature internally, we have a decreasing temperature externally. So for different instances of time, of course, the center temperature will decrease, so our temperature profiles will change in its shape, but the ratio between the internal and external temperature decrease remains approximately similar. Now, if we again introduce a parameter, now the temperature minus the ambient temperature divided by the center temperature, depending on time, minus the ambient temperature, we know at the center itself there's always a center temperature, so we have scaled it in that way that we always start here at the value of 1 with all of our curves, and on the outer side here on this axis we will not use the parameter x, but we will use the parameter 1 over the bio number, which gives us another scale for the problem. And doing so, all our curves collapse together, so we don't have different curves anymore, and we have a unified temperature profile. How can we utilize this information? So let's see here now the Heisler diagram for the internal temperature distribution. We have here on the axis the temperature minus the ambient temperature divided by the center temperature, depending on time, minus the ambient temperature, which means that if we have a value of 1 here, then we have always the center temperature which then means that our parameter x divided by x1 is the half of the thickness, and x is location from the center towards the outside. So this value is 0, and that's at the body center. So we have one other line that goes straight in a horizontal way. Now, if we look at different values of the ratio between the location x and x1, let's say, for instance, the maximum value x divided by x1 is equal to 1, then we are on the surface. And so we can see here on this graph the distribution of the surface temperature depending on the thickness of the object, or more or less depending on the bio number. Of course, we can see here that if we go to the right side and the 1 over bio, this parameter becomes larger, then we have a low bio number, which means that the resistance is on the outside, the temperature inside the body is nearly homogeneous, and we see that the different values all collapse to the one value. They all go to 1, so they all go to the center temperature. And vice versa, on the other side, we have a very low resistance on the outside, a strong or more relevant resistance in the inside. So we have a severe temperature distribution inside the object. That was the second part. Now we look at the third part, which is a time evolution of the emitted heat. So we see here on the axis that the total heat that is released from 0 to time t of the heat flux q dot integrated over time. And the total heat that is stored inside the object, it's Q0, and Q0 is also equal to the heat capacity times the mass times the temperature difference between initial temperature and ambient temperature. How can we do that now in the Heisler or dimensionless diagram? For this, we have the following diagram. We have the ratio between the heat that is released divided by the total heat that can be released. So the scale is again from 0 to 1, and on the x-axis we have the dimensionless time expressed by bio squared times Fourier. So we have the influence of the external resistance in this scale, and we have the influence of the temperature diffusion into the object towards the temporal temperature transport. So having these two values and now looking at different resistances or different value of the bio number, we can again have curves that describe the process, how the heat is released from the object. Now, in the slides I've shown, we have always looked at the case where we have, from the geometrical point of view, a plate. But that's not the only available diagram type. We have diagrams also available for cylinders, where the relevant dimension length scale is the radius, or we also have this for spheres. They are just a little bit different due to the different geometry, but the principle for the Heisler diagrams remains the same. Now let's finally, to the end of the lecture, look at a few examples. So we look at the quenching process of the steel plate. We have here our example from the initial slide. We have stainless steel here, we have oil on the other side. We have, of course, the properties of the steel. We have a heat transfer coefficient and the oil temperature of 30 degrees, steel temperature initially 700 degrees. The temperature profiles, of course, they will look like this. We will have a decrease of the temperature, and we will have the evolution of the temperature profile. Now, question first, after what time has the mean temperature or the center temperature cooled down to 160 degrees Celsius? To do that, we look here at the Heisler diagram, and we now have to check first for the ratio between internal and external resistances. So we take lambda divided by alpha times x1. x1 is half of the thickness here, so 9.25 millimeters, and we come up with the value of 4, or approximately 4. Now we can look at the diagram. We will look here at the value of 4, and we are interested in a temperature of 160 degree. 160 degree minus the reference temperature or the ambient temperature T oil divided by T0 minus T oil will lead to a value of 0.19, so approximately 0.2. Let's do that in the curve. Go down and we find here a value for the Fourier number of approximately 7. With a value of 7, we can calculate the time that it needs to cool down this plate, and this time is 158 seconds. The second question, what is the value of the temperature at the plate surface after that time? So we are looking now at this surface temperature. For this, we look in the other diagram, which relates the center temperature towards the temperatures inside the body. We are looking at the surface, so the ratio x divided by x1 is equal to 1. So we are actually here on this curve, and we still know that our value 1 over bio is approximately 4. So we can also go here to this value, to a value of 4, and we see that our value here is approximately 0.88, which is then the ratio between the surface temperature difference to the oil towards the center temperature difference with the oil. And from that we can calculate the surface temperature, which is 144 degrees Celsius. So the temperature drop inside the oil is much larger than the temperature drop inside the stainless steel because of the value of the bio number. Now the last part here is how much heat has been dissipated after this 158 seconds, or how much heat has been released to the oil. So we have here our total heat inside the system, and of course the remaining heat, and the dissipated heat is then the total heat minus the remaining heat. But what we will calculate anyway with the diagrams is the dissipated heat. So let's look at here the dissipated heat in relation to the total heat. We have the value of bio squared times Fourier. If we plug in the values of the problem, we have a value of 0.43. So we can use the curve here between 0.2 and 0.5. Here it's our value 0.43 approximately. And we have also this value given. So we can now look at the equation and we see that this ratio is approximately 0.75, which leads then to a ratio of 247.9 kilojoule per kilogram. So we still have the specific heat depending on the mass of the steel plate, which we don't know right now. This is the end of the video, so let's look at the two questions. So which two-dimensional numbers are used to describe the heat transient, the transient heat transfer problem with an additional external thermal resistance? So as soon as you hear the word additional external thermal resistance, you should directly think about the bio number, which scales the two resistances. And if you look at a transient process, the Fourier number has always something to say. Second question, which tools allow to determine the temperature profile or the amount of heat transferred for external plates, long cylinders or spheres? We have learned in this video that the Heisler diagrams can be used to calculate those parts. Of course, you can also use equations for that, but they are more complex, and for the sake of simplicity, especially for solving exam questions, we refer to the Heisler diagrams. Thank you for your attention and have a